This is your reality check.
Welcome to The Reality Check, the weekly Canadian show that explores a wide range of controversies and curiosities using science and critical thinking. Today is August 7th, 2020. I'm producer Pat, and it's just me as we continue with our COVID-19 format. We have two interesting segments for you today. Christina and I had a chat with friend of the show and TRC's fifth Beatle, Dr. Stuart Robbins, about the importance of studying impact craters, which is his specialty. Stu is a research scientist who studies planetary geophysics. But before that, we throw it to Adam, who brings us a segment about cans and coins during the pandemic. I hope everyone out there is staying safe and healthy, and we will talk to you soon.
What's up, cuboids? The COVID-19 pandemic has had an impact on a lot of goods, which have been difficult to find at retail. We talked about the toilet paper shortage a few months ago. Since then, I've seen bread, milk, flour, eggs, and even yeast shortages at my local grocery store. And while things seem to have been getting better recently, I've noticed some bare shelves lately. Now, I drink a lot of soft drinks, my favorite being a Mountain Dew. I usually buy cans on sale, but as I've been at home most days, I've switched to buying 2-liter bottles so that it's more cost-effective to drink. And another reason is simply because I haven't seen a lot of soft drink cans on sale for a good price since the start of the pandemic. While I used to be able to stock up when the prices were low, I haven't seen attractive prices in months. Suddenly, a couple weeks ago, I noticed something particularly alarming for me. No Mountain Dew anywhere. So was I being paranoid? Certainly for a single product to sell out, that can happen. But after visiting a handful of stores and not seeing a single can of Mountain Dew, and a shortage of bottles, I wondered what might be going on. My suspicions were confirmed a few days later when my local grocery store had a fully stocked soft drink aisle with no space for the Mountain Dew cans. And some other beverages also didn't have their own spots. They simply weren't there at all. A lot of Coke and Pepsi products, though. So what was going on? Now, I decided to rant a little on the internet asking if there was a Mountain Dew shortage, and one of my Twitter followers pointed me to an article about aluminum can shortages. Perhaps shortage isn't the right word, but we'll get into that. Now, the idea was simply that due to increased consumption of cans, certain beverage producers were having trouble keeping up with the demand, and so they were concentrating on their staples, like Coke, Diet Coke, and Coke Zero, and not so much on less popular brands such as Cherry Coke Zero or, in this case apparently, Mountain Dew. But were these articles to be believed? I dug around a little, and despite a lot of recent articles on the topic, I found the Molson Coors blog Beer and Beyond reporting on this back in May of this year. Their explanation was that as people were staying in due to the pandemic, the draft beer consumption dried up almost completely, instead being substituted with can consumption at home. So while bars that are now only starting to open with smaller crowds might serve a lot of beer from a keg or a bottle, a person at home is more likely to drink from a can. Add to this increased consumption of alcohol due to the pandemic, and the recipe for cans isn't that great. When it comes to soft drinks, we can expect similar trends. Restaurants are seeing a lot less business. Both sit-down restaurants and fast food joints will often use some sort of tap for their soft drinks, which is going into a washable glass or maybe a paper cup. Some of these might have bottles and some would have cans, but there's certainly going to be less can consumption in a restaurant than one might do in a home setting. Most people in their homes will drink from a canned soft drink, even though there's going to be bottles in there too. Even a bottled soft drink is something commonly purchased in a vending machine or a corner store, and it's generally more cost-effective to buy cases of cans when you're at home. The result is that vendors like Molson Coors can't keep up with the demand. A Coca-Cola rep similarly mentioned that aluminum cans are in tight supply. It doesn't take much to change the dynamics here. In the 8 weeks leading up to May 3rd, Consumer Edge Research reported a 27.2% increase in can sales. And so companies have decided to suspend production of slower-moving products and focus on faster-moving packs. There are certainly more cans being produced, but they still can't keep up with that demand. Though I didn't find many other people noting that there was a Mountain Dew shortage, I did find some people complaining that they couldn't find specifically Diet Mountain Dew. So this is the kind of thing which seemed to turn up a lot when people were talking about the shortage. A specific diet version of a beverage that might be less popular, so you can see why they wouldn't be selling that. Twitter user Sherry McGuffin asked Coca-Cola why she'd been having trouble finding Cherry Coke Zero. And they responded that they were seeing a greater demand for products consumed at home and were adapting to the demand. So, can this be categorized as a shortage? Well, it depends on how you look at the question. This isn't a matter of there being some issue in the production of a good. It's that consumption increased and the industry isn't keeping up. so there isn't a decreased supply, but there is still a shortage when considering the demand. Another metal commodity which has been harder to come by is coins. Some stores are having issues giving exact change due to what they are calling a coin shortage. But what's causing this? It's not so much a reduction in coin supplies, even though the US Mint has decreased production of new coins slightly. With so many coins in circulation, a short-term reduction in coin production should not account for a reduction in the availability of coins, as people have been seeing. The reason is a disruption in the normal circulation pattern of US coins, and so in this case, it's not accurate to call it a coin shortage because the coins are still out there, sitting in people's homes or pockets. They just aren't circulating as they usually do. Many businesses that take coins are seeing a reduction in business. This includes laundromats, vending machines, and car washes are all being used much less frequently. In general, retail sales are down in a number of ways, so people are not spending those coins at retail. These coins aren't being spent, and so they aren't getting back into circulation. The solution for a store may be as simple as asking for customers to use exact change so that they'll get the change that people have been unintentionally hoarding, rather than having to pay out more change to sit in someone's pocket. Cans and coins are just a few things that may be hard to come by these days. It's expected that as buying and spending habits change, there will be goods that will be harder to come by, and some of those reasons won't always be obvious until we dig a little to find out exactly why. I hope you're able to find the things you need for yourselves and your family. If you've got trouble finding something, it might be worth considering the reason behind it. I did end up finding some bottles of Mountain Dew at the grocery store, and I'm happy to say that the cans are back in stock at my local IGA. Peace out, cuboids.
Welcome back to the Reality Check, Dr. Stuart Robbins. How are you, Stu?
Oh, I'm just peachy keen, living the dream as your neighbor to the south who, well, let's just say it's summer, so I'd like to be in the north, but for more than one reason.
Right.
Oh, we can't wait until our borders open and we can have you back, but for now, this will have to do. You mentioned to us a few weeks ago that you were finishing up a white paper for the Decadal Survey on the importance of studying craters, which is, of course, your specialty. So we wanted to have you on to talk about it. What do craters tell us, and why is it important to keep studying them?
They tell us lots of things, and it's always important to study them.
Okay, end of show.
Yes, QED. Well, so actually, it might help if I back up very slightly and tell your listeners what the Decadal Survey is and what a white paper is. Even though we have talked about that a little bit, I hope that you're always bringing on new listeners, and some people might not always remember the subtleties of these things. So the Decadal Survey is something that I think is fairly unique to the United States and fairly unique to NASA as well. So first off, NASA is a federal agency that takes taxpayer money and doles it out to us deserving scientists to further the human cause in search of knowledge. And what that knowledge is going to be aimed towards, in other words, what these grant proposals should focus on, is the subject of these decadal surveys. So what happens is that every decade, and they're staggered because NASA has 4 different scientific branches. So right now what's up is the Planetary Science and Astrobiology Decadal Survey. So every decade, what happens is that NASA actually contracts with another federal agency, the National Academies of Science, or maybe Sciences, I don't quite remember, but it's the NAS for short. They contract with them, and they say, we want you to write a report that tells us what our focus is going to be for the next decade in this case, planetary science and astrobiology, for funding. So that affects things like what missions are going to be launched, what research grants are going to be awarded, and that sort of stuff. And so what happens is then the National Academies goes over to the community of scientists like myself, and they say, we want to hear from you on what you think the priorities should be. So what happens is then we sit down and we say, you should focus on our particular field, and our particular field deserves money. And then we write a basically opinion paper that explains why our field deserves money. And so what happened is last August when I was at the Planetary Crater Consortium meeting in Flagstaff, Arizona, a place that I hope to visit again in the, future and maybe bring you to along with me. It has things like the Grand Canyon and Painted Desert and other stuff, lots of mountains, volcanic.
I'm so down.
Yeah, it's nice. It's a nice area. Anyway, when I was at this meeting last August, we said, well, the Decadal Survey is coming up. We should write a paper that says craters are important. And I sort of volunteered to lead that effort. Then COVID-19 happened, and pretty much everyone who had volunteered to help write it said, nope, sorry, life exists. I have to do stuff. So 2 or 3 of us really hunkered down over the last couple weeks and wrote this paper. And what a white paper is it is more of an opinion paper than a scientific research paper. It's not peer-reviewed. That means it doesn't go to a journal and the journal sends it out and reviewers say, here's what you should change, here's what you should cite more, here's what you should get rid of, here's what you should add. It's really more of a paper that you write and then you basically submit it. In this case, the Decadal Survey white papers were limited to 7 pages, including references, and so it was a fun exercise in getting basically an opinion paper written in 7 pages and trying to say, this is everything you should fund in my field in the next decade. And we basically said, impact craters are important for everything in planetary science. Why? Because they are on every single planetary body that has a solid surface, except for maybe one. That one would be Io, which is a very volcanic moon of Jupiter. And it doesn't have any impact craters on it that we have observed, simply because Io is so volcanic that it resurfaces itself so quickly that craters don't stick around long enough for us to see. Again, sort of the importance of studying craters is they exist everywhere. They affect a planet's surface. And so if you want to know anything about a planet's surface, you have to factor in impact craters. And if we're sending any spacecraft anywhere in the solar system, you can study impact craters with those spacecraft. And you should, because there are still fundamental questions that we need answers to about impact craters. But we didn't just focus on that. We also had a section on the study of impact craters through in situ methods. So in situ is a fancy Latin term. I don't know the direct translation, but it basically means in place. That actually might be the direct translation. So this would be, for example, if NASA were to send a rover to Mercury. How could you study impact craters with a rover? Or just a lander? Or so we're recording on the 30th of July, and NASA just launched its next spacecraft to Mars, which is going to be a rover called Perseverance. But it also contains a technology demonstration piece, which is a helicopter kind of thing. Really, the technology demonstration for this little dual-blade Ingenuity craft can effectively a helicopter-like thing or a quadcopter-like thing, can that get us useful data? Is that worth funding in the future? So that's sort of what a technology demonstration is on these spacecraft. It's not actually tasked with returning real science. It's, does this technology work? But NASA has also selected a dual quadcopter called Dragonfly to go to Titan sometime in this decade, I think. So we again talked about how you can study craters with those kinds of craft as well. And then we had a section on the study of impact craters with laboratory experiments and simulations. And then we said, hey, we still can't actually simulate craters fully in a computer. And if we can't simulate craters fully in a computer, that means we're missing important pieces of information that need to go into those simulations in order to get what we see in reality. So all of those things factored into this paper, and really it is an opinion piece, but it goes through the process of the questions that we can answer in the next decade if NASA were to fund these types of missions where you can also study craters, and these types of research and analysis programs where you can study craters in the computer and in the laboratory and even do field work on Earth, because we have impact craters on Earth. And something that often gets neglected in funding because it's sort of a gap in terms of there is no specific program at NASA to fund this sort of thing, is those terrestrial fieldwork studies where you can go out to, say, Reese crater in Germany, or Meteor crater in Arizona, or I'm going to mispronounce it, Vreedfort crater in Africa. And there are lots of craters as well in Australia, basically every continent. And yet fieldwork funding to study those is still very much lacking in planetary science. And so that's what this Decadal Survey's purpose is it's to take all of these white papers, all of these opinion pieces, and then the panel has to whittle it down to a concrete set of recommendations for NASA.
So is the key point here, Stuart, that just the very nature of an impact crater, something that's like smashed into something, is exposing things that are below the surface, and then we can use that to understand the composition or understand maybe the age of?
So you want to get to the actual science. Yes, to both of your questions. So in this, we tried to say, okay, these are the open questions. This is why you want to study impact craters. It's not just a basic physics question of how do craters form, but it's also the question of impact craters tell us about ages of surfaces. The basic idea is if surface A has a lot of craters and surface B has very few craters, then A has been around longer in order to accumulate those. And so that's how we get ages. And so at a very basic level, impact craters are actually the only way we have to tell surface ages of anything around the solar system except for the moon and except for Earth. So that's one reason to study craters. Another one is studying individual craters. Pat, what you just said, they've effectively done our demolition drilling for us. So craters reveal layers in rock and layers in ice on planetary surfaces, and we can look at those layers and we can see what went on in the past on these different planetary bodies. And craters eject material, and they expose material from deep down. And so really, we can get at almost the mantle material. So in a planetary body, you have the crust, and then below that, I'm simplifying things significantly, you have the crust, below that you have the mantle, below that you have the core. Impact craters can actually dredge up material from the mantle if they're big enough. And that's the only way that we have of sampling material from the mantle. And so what we said in the white paper was one thing that these missions should focus on in the future is if they have spectrometers on board. So these are instruments that basically take the light, they break it up into individual wavelengths, and they study the brightness patterns in those wavelengths and can work out what materials those rocks are made of, or whatever was in that picture, what that was made of. And so we said, hey, you should focus these instruments on big impact craters. Those impact craters are revealing material from deep below the surface that we have no other way of studying other than by looking in these deep cavities created by these craters.
Now, Stuart, something you said to me is a little bit interesting. You said the number of impact craters would tell you or could give you some indication of the age of a body. But that seems really complicated to me. So I guess you would be averaging the number of craters of things in a general area, but space is really big. And then you have to consider the size of the object and the likelihood that they'd get hit.
Well, older planets would have, you won't see as many craters because a lot of it would erode, right?
So let's take the moon, because the moon is where we have the most data and what my 2014 paper is about. So what happens is the Apollo astronauts go to the moon and they bring back samples. And we date rocks from the moon that they brought back. And we say the surface in that area that the Apollo astronauts landed for that sample, the surface is that old. Then what we do is we go to geologic mapping. And geologic mapping is where you look at a surface and you say, this stuff right here is the same stuff as this stuff over here, but that stuff over there is different. And so you draw these boundaries and say, okay, all this stuff that's the same material and from the same, say, lava flow is going to be the same age. And hey, the Apollo astronauts happened to sample that. So we can say that that entire area is the same age. It's the age of this rock brought back by the Apollo astronauts. And then we can count the craters on that surface. Now, as you said, Pat, the craters are going to be lots of different sizes. So what we do is we create something called a size frequency distribution, which is a fancy term for a histogram. So the histogram is the number of craters on the vertical axis and the size of the craters on the horizontal axis. Then what we do is we say, what is the population of craters, the spatial density, the number of craters per square kilometer or per million square kilometers that is 1 kilometer and larger. For some reason, it's defined for 1 kilometer. I don't exactly know why, but it just is. So we say the spatial density of craters 1 kilometer and larger for this geologic unit is X. Then we go to another spot on the moon with more rock samples from the Apollo astronauts or from the Soviet Luna spacecraft. We count the craters, we plot them up, we look at the spatial density of 1 kilometer craters and larger there, and we say, okay, any area on the moon that has that spatial density of 1 kilometer craters and larger is going to be the same age as it is over here. And we build up this chronology curve, basically. And that chronology curve says, for this spatial density of 1 kilometer craters and larger, the surface is this old. We can only do that for the moon. We can't do that for Earth because, as Christina said, erosion happens. And we have different rates of erosion in different areas of the planet. On the moon, we don't have that. And so we can build this up for the moon. The reason we can only do this for the moon right now is because the moon is the only place in the solar system, other than Earth, where we have rock samples from a known location. And so we can tie those rock samples of a certain age to the surface that has a certain number of craters. And there were other white papers submitted to the Decadal Survey saying, we need more ages, because right now the lunar chronology calibration curve has maybe 10 data points, and there are big gaps in them. And it's only on the moon. So another Decadal Survey white paper I was on was doing this for Mars, and doing this for the asteroid Vesta. But it really needs to be done everywhere if we want to do this, because the only way that we can get from the moon elsewhere in the solar system right now is through models. And those models say, well, given how far you are from the sun and how close you are to the asteroid belt, and Kepler's second law, which is how fast things are orbiting around, because a faster projectile has more energy, so it's going to make a bigger crater. You have to factor in all these sorts of things, and the surface gravity of the body, and various other things. So basically, dynamical models, we have to use those in order to get the lunar crater chronology to anywhere else in the solar system. And we've done that. We've done that for Mars. We've done that for Mercury. We've done that for Mars moons. Some people have tried to do that for the asteroid belt and the outer solar system, but then the problem gets to the asteroid belt and the outer solar system are not hit by the same things that the inner solar system is hit by. In the asteroid belt, you have lots of different collisional dynamics happening, and outside of the asteroid belt in the outer solar system, you're mostly hit by comets as opposed to hit by asteroids. And it's not just comets from the Kuiper Belt or Oort cloud, it's stuff that orbits gas giant planets as well. So we call those planetocentric impactors because they are orbiting a planet itself and then striking the moons. And then we also have the Trojan asteroids. So these are asteroids that orbit with Jupiter, but they're 60 degrees ahead of Jupiter in its orbit or 60 degrees behind of Jupiter in its orbit. It's just the way that orbits work. The maths work. I think we actually might have covered it in 5 Minutes with an Astronomer, with Lagrange points. But anyway, the bottom line is that the solar system is dynamically messy. We don't entirely understand it, but it is the best thing that we can do at the moment. And scientists realize that there are lots of gaps in our knowledge. So it's not just my white paper that discussed this, but lots of others that said we need to better understand solar system chronology through whatever means are possible in the next decade, be it a mission that brings back rocks, be it a mission that can actually sample rock material and date it while we're there, or something else, be it better dynamical models. We need better telescopes in order to try to see what the impactors are in the outer solar system, because the only way we can do this is with telescopic surveys from Earth, where we look out and we see what these objects are, and based on their brightness, we estimate how big they are. But you can imagine these objects are really, really faint, and so we need better and better telescopes from Earth in order to do this. So Pat, your question sort of opened up a big rant or just a messy can of worms that I've now laid out to you. And if I can try to sum it up, it's basically that it's complicated. We can do it in a couple different ways, but really the best data are for the moon. And then we try to use what we know of on the moon to understand the crater chronology elsewhere in the solar system. But there are really big question marks and error bars on those numbers.
For show notes or to discuss this episode, visit our Facebook page and website at trcpodcast.com. For general inquiries or to send a topic or parody suggestion, email info@trcpodcast.com. Help support the show by leaving a review on iTunes and liking us on Facebook. Follow us on Twitter @TRC_podcast.